Dear students, under the lecture series on complex analysis, here we have a very significant topic, that is Cauchy-Riemann equation. In the examination, this question may be asked as state and prove the necessary condition for differentiability of a complex function. It may also be asked as derive the Cauchy-Riemann equations or state and prove the Cauchy-Riemann equation for a complex function. So now we shall see the statement of this theorem. Let f of z is equal to u of x comma y plus I multiplied with v of x comma y be a differentiable function at a point z. Then u of x comma y and v of x comma y have first order partial derivatives ux, vx, uy and vy at z, and these partial derivatives satisfy the Cauchy-Riemann equations given by ux is equal to vy and uy is equal to minus vx. So these are known as the Cauchy-Riemann equations, and ux, vx, uy, vy are first order partial derivatives. So by the definition of derivatives, we know that the first order partial derivatives are given by ux. So u is partially differentiated with respect to x, and so the limit will be with respect to delta x tends to 0. And since it is with respect to x, the difference will be here only for x. So u of x plus delta x, and y remains as it is, minus u of x comma y divided by delta x. Similarly, when v is differentiated partially with respect to x, by the derivative formula, we have limit delta x tends to 0 and v of x plus delta x comma y minus v of x comma y divided by delta x. In a similar way, we have uy and vy as well. So these we have by the definition of derivatives. So these are the first order partial derivatives. Now having this, we have to prove that uh, the function z, that is f of z, satisfies the Cauchy-Riemann equations given by u, u ux is equal to vy and uy is equal to minus vx. That is, the first order partial derivatives satisfy these equations. So that is what we are going to prove. So as the first step, let us write the complex variable z. So what is complex variable z is equal to? We know that it is equal to x plus iy. And what will be the small change in z? It will be delta z. And that is equal to a small change in x, so delta x, plus I. Small change in y is delta y. So this is the complex variable z and this is delta z. Now let us add these two. So what will be z plus z delta z? So z plus delta z will be equal to. We will add the real parts separately. So the real part is x over here and the real part is delta x over here. And so we will have x plus delta x plus I multiplied with the imaginary part is y plus here the imaginary part is delta y. So this will be z plus delta z. Now since f of z is differentiable, we have f dash of z to be equal to limit delta z tends to 0 f of z plus delta z minus f of z divided by delta z. This is by the definition of differentiable function. So since f of z is differentiable, this limit will exist. Now we shall substitute each of these terms over here. Now what is f of z from the question? So if you see here, f of z is given as u of x comma y plus I multiplied with v of x comma y. So let us take and write that. So I have taken and I have written here. Now using this, we shall write f of z plus delta z. So that will be equal to, first what we have here, the function u of x comma y. So for f of z, we have u of x comma y. What is this x and y? X is the real part of z, y is the imaginary part of z. So for f of z, we have to write u of real part of z, which is x, comma y, which is imaginary part of z. Now in a similar way, for f of z plus delta z, we have to write u of real part of z plus delta z. What is that? Z plus delta z we have here, and this is the real part. So x plus delta x, comma, imaginary part of z plus delta z, which is y plus delta y. So y plus delta y, plus I, and v of again the same real part of z plus delta z, which is x plus delta x, comma, imaginary part of z plus delta z is y plus delta y. So we have written f of z from the given statement, and using that similarly we have written f of z plus delta z. That is the reason why we found this z plus delta z over here. Now having these functions, let us take and substitute each of the functions over here. That is f of z plus delta z as this, and f of z as this in this, that is f dash of z. So from this, f dash of z, I will write here f dash of z will be equal to, so limit, now since we are changing to x and y, in terms of x and y, the limit will also change to delta x tends to 0 and delta y tends to 0. Since delta z tends to 0, delta x will tend to 0 and delta y will tend to 0. And then we have f of z plus delta z. So let us take and write this one. So what is that? U of x plus delta x, comma, y plus delta y, and then plus I multiplied with v of x plus delta x, comma, y plus delta y. So this is f of z plus delta z minus f of z we have to write, which is this one. So u of x comma y plus I multiplied with v of x comma y. So this is f of z. The whole divided by, so the whole divided by delta z. But what is delta z? It is equal to delta x plus I delta y. So we shall replace that also. So delta x plus I delta y. So we have substituted delta z as delta x plus I delta y from this. Now in the numerator, this is the real part and this is also the also real part. So we will combine these two real parts and write together. In a similar manner, this is the imaginary part and this is also imaginary part. So we will combine these two imaginary and we will separate the numerator as real part plus I multiplied with imaginary part. So we will write in that form. So from this we have f dash of z is equal to limit delta x tends to 0, delta y tends to 0. In the numerator, what is the real part? U of x plus delta x, comma, y plus delta y. So this one minus, we have minus here. So minus u of x comma y. So this is the real part plus I multiplied with the imaginary part we will write. Imaginary part is v of x plus delta x, comma, y plus delta y. And then we have a minus here. So minus this one, v of x comma y. So real part and imaginary part has been separated. The whole divided by, in the denominator, we will write it as it is, delta x plus I delta y. So this is what we obtain. Now this limit is common to both real part as well as the imaginary part. So we will take this limit separately and we will write real part from in the numerator plus I multiplied with whatever is in the imaginary part. In the numerator we will separate. Denominator is common to both the terms, so it will come as it is. We are separating only the numerators into real part and imaginary part. Okay, so this limit is in common, so we will take and write separately each of them. So as I have told you, I have separated the real part in the numerator plus I multiplied with. Since we had I in the numerator, I have written that I here, and the imaginary part I have written here for the numerator. The denominators remain as it is and they are common to each other, so it has been splitted and it has been written. Now here we will consider two cases. So what is the first case that we are considering? Suppose we are considering delta z tends to 0 along the real axis. So along real axis, we know that delta y is equal to 0 and delta x will tend to 0. So when we consider delta z along the real axis, we know that delta x tends to 0 and delta y is equal to 0. So having this, we shall now substitute over here. So what will happen to this? F dash of z will be equal to limit. Now since delta y is equal to 0, we will write the limit only for delta x. So delta x tends to 0 and then u of x plus delta x remains as it is, comma y. Now this delta y is 0, so we need not write it. So y plus 0 is y only. So x plus delta x comma y minus u of x comma y, the whole divided by, now delta y is 0, so this imaginary part will become 0 and therefore we will have only delta x. Similarly, plus I multiplied with, now here this one, limit. Now here also we will have only delta x tends to 0 because delta y is equal to 0. So what will happen here? We will have v of x plus delta x comma y. Because delta y is 0, we will have only y here, minus v of x comma y divided by, in the denominator this imaginary part will become 0. Therefore we will have only delta x because delta y is 0. So this is what we get. But as per the definition of derivatives, what do we know? What is this limit delta x tends to 0? Okay, u of x plus delta x comma y minus u of x comma y divided by delta x. That is what we have here. And what is that equal to? It is equal to ux. So this can be written as ux plus I multiplied with, what about this limit delta x tends to 0? V of x plus delta x. So limit delta x tends to 0, v of x plus delta x comma y minus v of x comma y delta x divided by delta x. So what is this equal to? It is equal to vx. So by the definition of derivatives, that's why I have written that separately and I have shown you. So it is vx. So therefore we have obtained f dash of z to be equal to ux plus ivx. So this one we will mark as the first equation. So this is equation 1. Now in a similar way we have case 2. That is, we are going to choose delta z tends to 0 along the imaginary axis. So how that will be? So suppose delta y tends to 0 and delta x is equal to 0. So that is, we are choosing delta z tends to 0 along the imaginary axis. So along the imaginary axis delta x will be 0 and delta y will tend to 0. So having this, now how it will become? Now this one will change to be, so f dash of z will be equal to, we will have limit, now delta y tends to 0 and delta x is equal to 0. So what will happen to this limit? It will be only delta y tends to 0. And then what we have in this, wherever we have delta x, it will become 0. So we will have u of x plus 0. So this will be only x. U of x comma y plus delta y minus u of x comma y, and this will be 0 plus I delta y. So I have written that here. Wherever I had delta x, I have equated it to 0, and the remaining I have taken and written in this. Plus I multiplied with plus I, and now again we will have this one where the limit of delta x will be equal to 0, so we need not write it. So we will have limit delta y tends to 0, and wherever we have delta x we have to put 0. So here it will change to be v of x comma y plus delta y. Other things remain same, and here this will become 0, so we will have only I delta y. So we will write it. So we have written it in that way. Now after this we see that this I and this I will get cancelled. So we have cancelled it. And so f dash of z will be equal to this I in the denominator we will write outside. So 1 by I. So what will be inside that limit delta y tends to 0, u of x comma y plus delta y minus u of x comma y divided by delta y. But what is that as per the partial derivative formula? We know that according to first order partial derivative, it is the partial derivative of u with respect to y. So if you check out this, you will know. So 1 by I, it will be u y plus, now since we have cancelled this I, what is remaining? This is what is remaining. Limit delta y tends to 0, v of x comma y plus delta y minus v of x comma y divided by delta y. So what is this actually? It is the partial derivative of v with respect to y. So v y. So that we will write. So plus vy. Now what is whenever you have 1 by I, that is I in the denominator, it has to be multiplied and divided by I. That's in order to get rid of this I, we have to multiply and divide by I. So this will be equal to I divided by I square. So what is I divided by I square? I square is minus 1, so that will be equal to minus I. Therefore 1 by I is equal to minus I. So that we will write. So f dash of z will be equal to minus I uy plus vy. So rewriting it properly, f dash of z will be equal to vy, which is the real part, minus the imaginary part is I uy. So this is the other form of f dash of z, so which is equation 2. Now we will compare equation 1 and equation 2 and equate them because both are f dash of z. We see that ux plus ivx from equation 1 is equal to, that is we are equating equation 1 and equation 2. So what do we get? Ux plus ivx is equal to vy minus iuy. So on comparing on both the sides, from the real part, we see that ux is equal to vy, equating the real part. So ux is equal to vy. While comparing the real part, we obtain this. And comparing the imaginary part, here is the imaginary part vx and uy. So we obtain uy is to be equal to, this is negative. So minus uy is equal to vx. So on rewriting it properly, we get uy is equal to minus vx. So this is by comparing the imaginary part. So we have obtained the required CR equations, that is Cauchy-Riemann equations. So as per the statement, the first order partial derivatives have satisfied the Cauchy-Riemann equations ux equal to vy and uy is equal to minus vx. So hence we have proved. So I hope you would have understood how to prove this Cauchy-Riemann equation. This is a very significant problem which has appeared in many previous year question papers. So kindly go through it patiently to understand it better. And in our upcoming video lectures, we will solve problems under this topic. Thank you.